Okay, so this is our very last chapter, chapter 12. Okay, so let me just, all right, and chapter 12 is all about correlation and linear regression. Okay, all right, so maybe just a little bit of talk about I guess, our next week and whatnot. So this is our last week of kind of new stuff. On Tuesday of next week, we'll spend time in review, and then on Thursday we will have the final exam. So the final exam is going to be synchronous. So this will be kind of like the one time where I'm going to require everybody to come to class at our designated time from 4 to 5:50. The exam will be taken, on Gradescope, much like the quizzes. The only difference is that you'll be signed into Zoom, and you will have your cameras on. I won't be recording or anything, but the cameras on thing is kind of to kind of make sure that you're taking the exam by yourself. I don't think there's like a widespread problem of this, but I have heard stories of, students kind of getting together with classmates or friends and taking the exam together, in the online setting. And so to kind of discourage that, we're gonna do it synchronously from 4 to 5:50. You'll be signed into Zoom with your cameras on, and then you'll just take it on Gradescope. Also, if you have any questions during that time, you can ask your questions via the chat on Zoom, and I can answer them as well. I'm still trying to figure out the exact exam length to put forth, and so that's always kind of a challenge as a teacher, to try to find the kind of the sweet spot of writing an exam that's of appropriate difficulty and appropriate length. And so I'm working on that for the final. And yeah, the final is cumulative. I would say a much stronger emphasis on stuff from chapter 6 and beyond. So mostly on statistical inference, a lot less stuff on kind of like the foundational things like probability and probability distributions and stuff, because everything after chapter 6, uses those earlier chapters to build off. So if you're able to do the later chapters, then I'm pretty sure you were able to do the earlier chapters as well. So so the final exam will be cumulative, but I would say a much stronger emphasis on things from after chapter 6. Okay, chapter 6 and later. And then so I sent out a message kind of extending the due date for lab 4. Lab 4 is due Friday rather than yesterday on Wednesday. And then lab 5 has been assigned, and if you've taken a look at lab 5, there's no R involved. There is an article for you to read, and then you'll answer questions about the article. And my hope is that, so the article is it's from a medical journal, and it was, so I don't know if you remember last year around this time, there was a lot of kind of talk about hydroxychloroquine as a possible treatment for COVID-19, kind of touted by certain peoples and whatnot. And well, anyway, the medical research article goes into and tries to see how effective hydroxychloroquine is as a treatment for COVID-19, and the results are given there. And my hope is that, from taking this course, you'll be able to read the statistical methods section of the article and understand what they're talking about. That same medical journal has also recently published an article on vaccine efficacy, which I think is also interesting. But there are a few kind of statistical topics in that article that we haven't really covered in the class. So I didn't want to kind of ask you too many questions about it. So, but anyway, it's interesting, and you can read it, and I think it's very relevant to our life and our world right now. There's a question in the chat. Is the final going to be open notes? Yes, the final exam is open note and open book, just like all of the quizzes have been. So the quizzes and the final, everything open note, open book. I just don't see any kind of effective way to kind of even police a policy of saying like, you're not allowed to look at your notes. And I don't even know if that would even be enforceable in any effective manner. So we'll just go ahead and make it open note. And I think that's totally fine. The truth is if you're going to be doing any kind of statistics in the future, probably you'll have some reference materials to look at. Okay, any questions before I get into today's content on correlation and linear regression? Okay, so one last thing. I've got a favor to ask of you, and that is to fill out your course instructor and course evaluations. So I think those are available, and you can kind of wait. I think the deadline is probably sometime next week or whatever, but I actually don't know when the deadline is. But those like my supervisor, my boss looks at those and things like that, and so they do make a difference. And the one question that is kind of the most important, I think, is the second to last question is like, what's your overall rating of this instructor? That's the one question that matters the most. Okay, so the deadline is 8 a.m. Tuesday. Okay, so yeah, I do want to request that you fill those out, and the question that they kind of look at the most carefully is the one that says, what's your overall rating of the instructor, and then what's your overall rating of the course? I know they ask a bunch of other questions like, what's your rating of instructor concern? And I don't remember what else they ask, but the two most important questions are, what's your overall rating of the instructor, and what's your overall rating of the course? I hope you've enjoyed the course, and I hope you've enjoyed having me as a teacher. I've enjoyed teaching and being your teacher. And so, I hope the feeling is mutual here, but whatever you're willing to put there in the course evaluations is appreciated there. Okay, let's talk about correlation and linear regression. And this whole chapter is about kind of exploring potential relationships between numeric variables. All right, so far, everything else, we've either had categorical variables. So when we did chi-square tests, we had a chi-square test for independence, you had two categorical variables. When we did ANOVA and t-tests, one variable is numeric and the other is some kind of grouping variable, which is a categorical variable. And today, we're going to look at two numeric variables. Is there a relationship between two numeric variables? And so the idea here is the observations in your data have multiple variables recorded, right? So the observations have info recorded in multiple variables. Okay, and then at least two are numeric. Okay, and so, just a silly example. So we could have, let's say, do information on some snakes or something, okay? And so you could have, names of the snakes, and then we can measure the length and the weight, and what other information you might want to record, sex, some other variable, color, something like that. Okay. And I don't know, what are some snake names? You have Nagini and I don't know what's Sal. We'll just make Salazar and whatever. Okay, so anyway, we're gonna just I'm just making some information up. Okay, so we'll say we have a snake 60 centimeters long, weighs 136 grams. I have no idea how long a snake is or how much it might weigh. We'll say 69 centimeters, weighs 198 grams. I don't know, some other snake maybe is 66 centimeters and weighs 191 grams or something. Okay. And what we can do is we can create a scatter plot. All right. And I think you guys are familiar with scatter plots. And so along one axis, we will put the variable length. And on the other axis, we will put the variable weight, right? And basically, you will just kind of plot these, right? So you'll say like, okay, so here's 60 and, blah, blah, blah. I have no idea, right? And so we'll just kind of put a dot here, and then we'll say, here's a dot that goes up here, and then another dot. And basically, we can just kind of plot the different snakes as, each observation that we have will appear as a dot in our scatter plot. Okay, and really the whole essence of today's lecture comes down to this, right? We're going to ask a question. Is there a relationship between a snake's length and its weight? Or, between one variable and the other variable, right? A snake's length and its width, right? Okay, and then our answer was what? Snakes that are longer tend to weigh more than snakes that are shorter. Okay, so we're just going to look at this and we'll say, oh yeah, when the snake gets longer, its weight goes up. When the snake is shorter, its weight is lower. And pretty much our answer is snakes that are longer tends to weigh more than snakes that are shorter. And that's pretty much what we are trying to do today, okay? Except, rather than just having this vague statement that says longer snakes weigh more, we're going to try to quantify that. We're going to try to say specifically, if a snake is 1 centimeter longer, it's going to weigh 1 gram more or 2 grams more or something like that. We're going to try to quantify the exact relationship. Okay. But effectively, this is what it comes down to, right? We're trying to establish some kind of relationship between two numeric variables. Okay. So as we get into this, we're going to see a few names for the variables. Okay. Well, I think our textbook prefers to use some of these names. So we've got our X variable and we have our Y variable. Okay. And so here we often call X the explanatory variable, and Y we will call the response variable. Okay. Sometimes we'll call X the predictor variable, and Y will be the predicted variable. X, sometimes in some books, they'll call this the independent variable. This is my least favorite name. And Y will be called the dependent variable. Dependent variable. So this is my least favorite. Just because back when we cover probability, if one thing depends on if two variables are dependent, if A is dependent on B, then B is dependent on A. And it's just kind of, I don't know what they're trying to say here, but somehow, I don't know if this is good, right? This is, okay. And sometimes, X might be called the input variable, and Y will be called the outcome or output variable, right? All right. And in all of these, whatever names we choose, and it probably differs from textbook to textbook, but the case is that we will use the X variable to explain or predict the Y variable. Okay. And when we talk about explain or predict, okay, the word explain does not mean explain the relationship of like why or how it works, okay? And it's not some kind of cause and effect relationship, right? So when we say X explains Y, we're not saying, does not mean that we can explain the nature of the relationship or explain, I'll say, explain how the variables interact or some kind of cause and effect relationship. Okay, all we're saying is that using the X variable can help us improve our prediction of the Y variable, okay? Explain simply means that using our X variable use the X variable to improve our prediction of the Y variable. Even if it's just a slight improvement. Okay. And so, if we're doing snake length, is X and snake weight is Y, what we can do is, well, first of all, if we know nothing about the snake and we were asked to make a prediction for the weight of the snake, what shall we predict? Has to predict its weight. Okay, so if you know nothing about the snake and you're asked to predict its weight, the best guess is to just predict the mean, y bar. Okay, so if you have your data and all of the other snakes have an average of, say, 180 grams or something, then at that point, your best guess for how much the snake weighs, if you know nothing else about it, is just to predict the mean, 180 grams. We'll call it the safest guess. Y bar. Mean weight. Okay, so that would be kind of the best guess to predict if you don't know anything else about the snake. But if you know, if you're told that this snake is longer than average, then what we would do is we would adjust our prediction and probably predict a weight that is higher than average. Okay. And so the fact that we would make that adjustment means that knowing the length helps us improve our prediction of weight, or that X explains Y, okay? So if we're told that the snake is longer than average, we would adjust our prediction. And we would predict that the weight is going to be above average. Okay, so because we adjust our prediction, we can say X explains Y. Our prediction of Y based on X . Okay, so that is kind of the idea of using one variable to explain or predict the other variable. Okay, and again, we're not able to establish any kind of cause and effect relationship. We're just saying, hey, if the numbers in X are greater than average, then we're going to predict that the numbers in Y are going to be greater than average. Okay, so let me talk about describing a relationship between two numeric variables. Okay, first we would describe the form or shape. Okay, and this will be linear versus nonlinear as far as this class goes. Okay, so as far as the form or the shape, we're either going to say the relationship is linear or the relationship is nonlinear. Then we can talk about the direction. And then we can also talk about the strength. Okay, so let's talk about form. So as far as form goes, just draw. Right, I keep getting this sticky keys. All right, so here I've got X, I've got Y. So here on this side, we will have linear relationships. And linear basically means like when you draw some dots, you know, they form something that looks kind of like a straight line. And there can be like more spread and scatter, but overall, we can draw some kind of line through it. Whereas if you have something that's nonlinear, you might have something, something that looks like that. Something that looks like that. You might even have something that looks like this, right? So here, relationships, nonlinear relationship. Okay, relationships do exist, but they cannot be explained by a straight line. Okay, whereas over here, a straight line, captures the essence of the relationship. And as far as our class go, we're just going to look at linear relationships. Okay. So today's tools only work for linear relationships. All right. All right. And so the key is graph first and decide if the relationship looks linear or not. Okay, so graph it first and then decide if it looks linear or not. Our eyes are very good at detecting and deciding if things look like a straight line or something else. Okay, so that's describing the form or the shape. Okay, all right. Once you decide it is a linear, we can talk about the direction of the relationship. Okay, and so as far as the direction, we will have positive, okay? And positive means the overall trend is that large X goes with large Y. And small x goes with small y. All right, and so an example, snake length and snake weight. Longer snakes weigh more, large X goes with large Y. Shorter snakes, small X goes with small Y. Shorter snakes will weigh less. Right? And so the picture might look something like this. Let me just put some dots here. Okay, so we'll call this, here's X and here's Y. And this part of the graph, we have large X, and that goes with large Y, right? And down here, we have small x, and that goes with small y. Great. Okay. Then we also have the negative relationship. All right, and the overall trend for negative relationship, just kind of the flip of this. Large X goes with small y, and small x goes with large y. Okay, so an example here, we'll do, we'll say used car mileage and sale price. Okay, so if you're ever shopping for a used car, what you will find is that cars that have a larger, have more mileage, right? So you might find some cars that have like 15,000 miles driven on it, and you might find some cars that have like 100,000 miles driven on it. Okay, so in the cases where you have a car with low mileage, okay, so you have small x, they generally sell for higher prices, large y, okay? Cars with lots of mileage, okay, like 120,000 miles or something. So large X, generally, their sale price will be lower, okay? So large X goes with small y, and you'd have a negative trend. And of course, there's other factors that go into the cost of a used car, but the age and mileage of a vehicle is a pretty strong predictor. Of course, you know what model is it, right? A Honda Civic versus you know, a Mercedes G-Wagon or something is going to be quite different. But the overall, you know, if you look at within some model, then this kind of overall trend of more mileage, lower price is going to hold true. Okay, and then you also have so we have positive direction, negative direction, and we'll say direction is neither positive nor negative. And you can have many different forms of this. Okay, so let me just draw a few of these things. All right, so here we'll do age and how many fingers. All right, and for most people, this plot is going to look like this. You know, you're born with, for most people, born with 10 fingers, and as they age, the number of fingers they have does not change, and so the direction is neither positive nor negative. Okay, we could have, say, time on the x-axis versus altitude of rocket. We'll do a toy rocket, not one that's carrying a billionaire or something. And this will look like this, right? So if you launch a toy rocket from the ground, it'll go up and then it'll come back down, okay? And, you know, there is definitely a relationship but it's not linear, right? Relationship, but it is not linear. And large values of X are associated, we can't say that large Y goes with either high or big, or really it's like low values of Y, okay? Does that go with large X or small X? And it's not linear, and we can't make general statements about large X and large Y, right? Say, okay. Is the constant one considered linear? Linear is not the right word. It looks like, it looks like a straight line, right? But it's just the answer is no relationship, right? So we use the word linear to describe something where you do have a relationship, and that relationship is described by a straight line. But for this one with the how many fingers and age, there's just no relationship between how many fingers someone has and their age. There's just the relationship doesn't exist, right? And in fact, if we flipped the axis, right? If we flipped the axis and we said, if we swapped X and Y and we put X on the, number of fingers on the X-axis, and we say, okay, if I tell you how many fingers somebody has, can you predict their age? Also, no, right? That's not going to work, right? And you say, oh, somebody has, I met so-and-so and this person has 10 fingers. Can you predict this person's age? And the answer is no, right? There's no relationship there. So a straight vertical line, also no relationship. Okay, and then the last one, this one's just kind of silly, but sometimes you'll have something like shoe size versus GPA, okay? And here, you're gonna have people with big feet that have high GPAs and people with big feet with low GPAs. You're gonna have people with average sized feet with high GPAs and low GPAs. You're gonna have people with little feet that have high GPAs and low GPAs, all right? So there's just no real relationship there either, okay? No relationship that might appear as a cloud of points. All right, is that okay? As far as direction, positive relationships, negative relationships, so on and so forth. Okay, and so the last bit is the strength. Okay, and the strength is basically how good will our predictions be? Also, how much scatter? That's pretty much how we answer the strength of a relationship question. So here we're going to have a couple graphs here. And so you might have, let me do this. So both of these will draw some kind of positive trend line. All right, and one, we'll put very little scatter. And over here, we'll put lots of scatter around. Okay, so overall, the trend for both of these would be linear, positive. Okay, and this would have strong, and this would be weaker. Okay, less scatter. And then a prediction for X, right? So if we predict X here, our prediction here predicted Y, we're going to call this Y hat. Predicted Y, how good is my prediction? Okay, over here, there's a prediction based on X can be expected to be accurate. Whereas over here, you have more scatter and predictions based on X. The value could be, above or below, right? So predictions based on X might not be as accurate or precise. Oh, sorry. Thank you. Thanks for the reminder about the view quiz answer. Let's go ahead and give you your first view quiz answer. The first view quiz answer today is the letter B. B as in bear. B as in bear or ball. Okay, B. Okay, so that is, those are kind of the conceptual ideas. And rather than just saying, oh, okay, the relationship is strong, the relationship is weak, okay, just like we have the standard deviation to quantify the spread rather than saying lots of spread or little spread, we have another statistic, this one's called the correlation, that will quantify the strength of a relationship and the direction, okay? So we quantify the strength and direction of a linear relationship with the correlation. So rather than just saying strong relationship, weak relationship. We give a number. I guess the full name is the correlation coefficient, but we just call it the correlation, okay? And it's technically Pearson's correlation. There's you have other correlation. You have Spearman and Kendall's correlation, but not to worry. When we talk about correlation, almost always Pearson's correlation. The symbol is R. Okay. And R is always, or the correlation is always between positive and -1 inclusive. +1, -1 inclusive. Okay. And the sign of R is the direction. Here, I'll just also write. Okay. Okay, so R greater than 0 is positive relationship. R negative would be negative relationship. Okay. And if R is close to 0, the relationship is weak. And if R is far from 0, that is close to 1 or -1, the relationship is strong. Okay. Now, these interpretations only make sense for linear relationships. Okay, and the issue is that, well, and it's an issue, but R is also, the correlation is just the result of a formula. So you can take points from a nonlinear relationship, plug it into the formula, and you get a number back. But that number is not going to have meaning, okay? So you can plug in points from a nonlinear relationship and into the formula, I should say. And you'll get a value. Okay, but it won't be useful. So I guess the kind of the flip side of this is that just because you have a value for correlation doesn't necessarily mean that the relationship is linear, okay? Or just because you can calculate R doesn't mean you should. Okay, and I'll write this again. Always graph first to see if the relationship is linear. Okay, so let me just show you a couple graphs and pictures of stuff. Oh, here's a little thought exercise. Again. This. Okay. All right, so here I'm going to put dots. So these dots are supposed to be exactly on this line. And the question is, what is the value of R? What do you guys think the value of R? Okay. So we have the direction is positive. What is the strength? Strength, very strong, very, very strong, no scatter, okay? Very strong. We have basically no scatter. So this is going to be as strong as we can possibly get. The R here is going to be +1. So you have that correct. So R is +1. Okay, here is another plot. Okay. What do you think R is here, right? So this one, we had an R of +1, and now we have a line that looks like this. What is the R here? You think it's less than 1, 1, 0? Okay. R here is also 1, okay? So the direction is positive. And no scatter. All right. So it's a common mistake because you see the slope, and the slope is like way low, right? And so I intentionally did this to get you to think about this. And the correlation has nothing to do with the slope. Okay. Correlation is unrelated to slope. Okay. So So it's not weaker than the first one because basically in both plots, there's no scatter, right? And the correlation is a measure of the direction and the amount of scatter. And both plots have no scatter. So that's going to be the strongest possible relationship. Okay, no scatter is basically the strongest possible relationship would be either +1 or -1, depending on the direction. Okay, no scatter means strongest possible relationship. Okay. Let me try. Oh, that's not what I wanted. Okay. Never mind. All right, what about this last one here? What is the R for this? Oh, sorry. I'm going to have dots exactly on the line here. Yeah, for this one, R is equal to 0. Okay, there's still no scatter, but the direction is neither positive nor negative. All right, and so this sometimes makes students feel a little bit uncomfortable because it's kind of like, you know, these are all have R equal to 1, and then suddenly as soon as it becomes flat, it becomes 0. And then as soon as there's a little bit of downward angle, it suddenly becomes -1, right? So if it has a negative slope and there's no scatter, it would be -1. Yes, that's correct. And you know, it just feels like there should be a little bit more of like a smoother transition from +1 to 0 to -1 or something like that. But what we're doing is we're actually describing a relationship. And here we're basically saying there's no relationship between X and Y. Like no matter what you plug in to X, and is it going to change what we predict for Y? And the answer is no, it's not. It's not going to change what we predict for Y. And over here in both of these cases is that as you put in a bigger X, you will get a bigger Y. Your prediction, you know, you put in a bigger X, you'll get a bigger Y. So this could just be like how many minutes have passed and how long are your fingernails, right? And it's like you could put in like 1 more minute or something, and if we had a super accurate way of measuring your fingernail length, like yeah, it grows, right? It grows every day. Your fingernails grow just a tiny bit, and if we had a way to accurately measure the exact length of your fingernail, like yeah, we would see a very slow slope or very shallow slope, but we would see that number getting longer, right? Whereas this is going to be something where it just doesn't change. Okay. Oh, this thing happened again. It's like there's like a button on my mouse that if I accidentally tap, where did my I need to, there's a picture I want to copy. Nova chapter. Oh, okay. Here we go. Okay, this is the picture I want. Let's copy this. And so here's a bunch of scatter plots. That I think show what I want to show. Okay, and this, so you can see as we have more and more scatter, the amount, our correlation goes lower until we get to 0 where there's total scatter. And over here we have -1. Here we can see the slopes don't affect. When it's flat, we have 0. And these are a whole bunch of pictures where R is equal to 0. Okay. Now, one thing that you might encounter is you might encounter something that looks kind of like this, right? So this could be like your toy rocket, and maybe something happens and you don't get any data points down here. And if you can plug these values into R, this would be wrong, right? But you can plug the values into R and plug the values into the formula, and you'll get an R, okay? What value would we get? Okay, well, I told you it's not a linear relationship, but in this case, what you might get is, like if we had to summarize this with a straight line, it might look something like this, okay? And so your formula, R, is going to spit something out like, I don't know, 0.65. I'm just making this number, okay? R would be positive because for this data, if you had to use a straight line, it would look something like this, okay? But again, you get a value for R, but this value does not carry meaning. Have a useful meaning. Okay, so there you have that. Okay, so you can plug numbers in, and it's going to spit something out because it's going to just say like, oh, if these were kind of the points, and we're assuming there's a linear relationship, then yeah, I guess R would be something like 0.65. But again, it's not really a useful number. Okay, let's talk about calculating R by hand. Now, I have to confess, we're going to learn how to calculate R by hand. But the truth is, nobody really does this, okay? So no one really calculates R by hand, but I think there is some merit and there is something you can learn from calculating R by hand, okay? So that's why we do it. But again, confession, no one calculates R by hand. All right, so the formula is this, okay? R is, you basically take the z-scores for X and you multiply it by the z-score for Y. And you do this for every observation, and oops, I left off, I'm sorry. You have to sum them up, okay? So I apologize. You take your z-score for X, your z-score for Y, you multiply them together, and then you sum them up, okay? Now, the z-score, if you remember, the z-score is basically each value. So I'm going to do each value xi minus the mean of X divided by the standard deviation of X. And the z-score for Y is the same thing. Each observation of Y, subtract off the mean of Y, divide by the standard deviation of Y, okay? And the standard deviation of X and standard deviation of Y is going to be the same for all I observations. So this technically goes from I from 1 to N. And so the correlation can also be calculated this way. We're going to do 1 over N minus 1 times 1 over the standard deviation of X times 1 over the standard deviation of Y times the sum of each X observation minus X bar and each Y observation minus Y bar. Okay, so this will be kind of our formula that we're going to use. Okay, so here is a data set. We're going to have a very simple data set. And kind of just make a little chart here. All right, so I've got X, I've got Y. My observations are 1, 2 for this first one. The next one is 2, 6. The next observation is 3, 4. And the last observation is 4, 8. Okay. And we're going to calculate the summary statistics of each column. Okay, so the mean of X, if I add these four up, I'll get 10 divided by 4. I get 2.5. And then the standard deviation of X, and again, you just kind of take the regular old standard deviation formula. I'm going to just, I've computed this out. You get 1.291. Okay. The mean of Y, if you add these four values up, you get 20 divided by 4. The mean of Y is 5. Standard deviation of Y is going to be 2.582. All right, so these are just the summary stats of each column. All right, and so what we're going to do is we're going to calculate each value, xi minus x bar here. We're going to take each value, subtract off the mean. So I'm going to do 1 minus 2.5. I get negative 1.5. 2 minus 2.5. I get negative 0.5. 3 minus 2.5. 0.5. 4 minus 2.5. Get 1.5. Okay. And then we'll do the same thing over here, but with the y's, we're going to take each observation y, subtract off the mean, 5. So we're going to do 2 minus 5, get negative 3. 6 minus 5, I get 1. 4 minus 5, so I'm just taking each value in y, subtracting off the mean. I get negative 1, and then I do 8 minus the mean, 5, and I get 3. All right. And then now I'm going to multiply these two columns together. Xi minus x bar times yi minus y bar. Okay, so I'm going to have negative 1.5. So I'm going to take this column, multiply by this column. And here I get positive 4.5. The next value, I have negative 0.5 times 1. I get negative 0.5. Then I have positive 0.5 times negative 1. I get negative 0.5. And then lastly, I have 1.5 times 3. And I get 4.5. All right, let me just kind of pause there for a moment and just make sure everybody's okay with how I got the values in every single one of these columns. Okay, all right, well, I got 1 thumbs up there, so 2 thumbs up. Okay, we'll consider this a success then. All right, okay, so this gives us our thing, and so what we're going to do is we're going to get the sum, right? So the sum of this column, sum of the column. So we're going to add these up, 4.5 minus 0.5 minus 0.5 plus 4.5. Well, the two 4.5s add up to 9, and the two minus 0.5s add up to a negative 1. So this will add up to 8.0, okay? And so basically this part right here, this part has added up to 8.0, okay. All right, and so the formula R is going to be 1 over n minus 1. We have 4 observations, so we're going to do 4 minus 1 times 1 over the standard deviation of x, 1.291, times 1 over the standard deviation of y, which is 2.582. Okay, and then we're going to multiply by the sum, which is 8.0. And so if you plug all of these in, oh boy, you're way too big, calculator. Okay, so we'll do 8 divided by 4 minus 1 is 3. We're going to divide that by 1.291, and we'll divide that by 2.582. Okay, and well, it's 0.7999 here, but it's 0.8. Okay, 0.8. Our correlation. It's 0.8. All right, and that's how we got this number. How do we feel about that? Okay, all right, great. Thank you. Thank you for those thumbs up there. All right, and so, what I want to kind of show here is, here, let me just create this, no, not this one. Let me open up R here. And so here, let me copy this picture. And the idea is, again, here, let me just write out my X and Y observations. We have 1, 2, 2, 6, 3, 4, and 4, 8. Okay. And here, what I've plotted in blue here, this is X bar, which is 2.5. And this is Y bar, which is 5. Okay. And remember what we talked about, the what it means to have be positive or negative direction, right? So positive direction, you know what, I'll we'll put in blue here, okay? And so we can look at this first observation, okay? This first observation, 1, 2, is like far below the mean, okay? So this observation, okay? So it's much lower than X bar, okay? And it's much lower than Y bar. Okay, so this is small x goes with small y, right? That's so this will contribute positive, right? So this has a large positive contribution to R. Okay. Over here, let's look at our next observation. Right. This is it's below the mean. Okay. So what is that? That's 2, 6. Okay. So lower than X bar, but above Y bar. Okay, so this is going to be small x goes with big Y. Okay, but it's only slightly below the X, and it's only slightly above the Y bar, slightly below X bar and slightly above Y bar. So this is going to have, so this is in the negative direction, right? And so this will have a small negative contribution to R. Okay. If we look at this one, it's kind of the similar thing. We're going to have a small negative contribution to R. Okay, because again, this is the observation 3, 4. It's slightly above X bar and slightly below Y bar. So the direction is negative because it's large X goes with small y. Okay, because we're above X bar, but we're below Y bar, right? And then over here, okay, and then this is just kind of the opposite, large X large X, large Y. So that's going to have a large positive contribution. Okay, and so overall, the positive directions, the positive contributions outweigh the negative contributions. So our overall correlation is going to be positive. It's net positive. All right. Okay. So we can kind of see that's what happens when we calculate the correlations, right? Because I think when we did it as far as the xi minus x bar times yi minus y bar, it was something like 4.5, negative 0.5, negative 0.5, and 4.5, right? So we have big positive contributions and small negative contributions. And so overall, when we add them up, we end up getting something around 0.8. Okay, and so, you know, if we were to just kind of imagine some data okay, that so if you had some data set that looks like this, then we would see that the correlation here would equal 0, right? Because if I were to draw my arrows, we would see we have positive contributions in that direction. These are all supposed to be the same size, and negative contributions in this direction. And we could see that they would all kind of cancel each other out. Right, so if we did this, we would end up having the positive correlations and the negative correlations would cancel out, right? Positive contributions in blue. Cancel out. Negative contributions in red. Okay. And so, you know, calculating the correlation by hand in that way, I think, reveals a little bit about how why exactly we get the numbers that we get. Okay. All right. Let me give you your second view quiz answer. Today's second view quiz answer is the letter D. D as in dog. D as in dog is your second view quiz answer. Second view quiz answer. D as in dog. All right. So we do have, there is a hypothesis test for significance in correlation, or significance of correlation. So let me this back. All right, so here we have 4 data points, and we have R equal to 0.8 for the 4 data points. Okay, and what we want to know is that, is this correlation significant, right? Correlation can be anywhere from -1 to +1. And basically, we want to know is it significantly different from 0, right? So if our sample were drawn randomly, from the population, does our sample provide evidence that the correlation in the population is not 0? Okay, or another question, is 0.8 significantly different? Significantly. It's like I have to sound things out. Okay, is it significantly different from 0? And I guess the kind of the flip side of that is it possible that the population has no correlation and we got this just by random chance? And we got these 4 points by random chance. R equal to 0.8. Chance. All right, what do you guys think? You think 0.8 is significantly different from 0? Yes, no, maybe? Okay, so when we write hypotheses, we write rho equals 0, and then the alternative is going to be rho does not equal 0. I know it looks like a P, but this is rho. Rho is the correlation in the population. It's the Greek letter that corresponds to the letter R. So you have R for correlation, and you have the Greek letter that corresponds to it. So rho, correlation in the population. It looks like the letter P, but it's rho. Okay, and so here's what we have. We got rho is 0, rho is not 0. Okay, or it could be directional. Rho greater than 0 or rho less than 0, whatever, etc. Okay. I guess in words, your null hypothesis would be there is no correlation between X and Y in the population. Okay, so we're going to do a p-value calculation, right? We got to calculate our p-value. And so the p-value, again, would be the probability of getting our data. So it would be the probability of getting R equal to 0.8 or something more unusual, which would mean which would be R greater than 0.8, or if because it's non-directional, we'll say R less than negative 0.8. Okay, by random chance. So it's the probability of getting something more unusual by random chance if the null hypothesis were true. Meaning there is no correlation between X and Y in the population. All right, what do you guys think? No one really responded. Do you think our correlation is significant? Yes or no? You guys are you guys able to use your reaction yes or reaction no? Or thumbs up for yes, I think it's significant, or something? Okay, all right, 3 people have responded. Okay, oh, okay, look at that, 10. Now when I go to you guys respond. Okay, so we got about 14 yeses and 1 no. Let's let's calculate this out, okay? So our test statistic, okay, and I'm not going to get into any like the theory behind how we got this test statistic. I will just tell you this is the formula that we use. It's a t statistic, and this is it, okay? And what you do is you crunch this out. N is kind of the number of observations, right? R is your correlation. And you'll look this up in the t table. With n minus 2 degrees of freedom, okay? And it's minus 2 because 2 lines define a straight line, or 2 points define a straight line. So if you have 2 points, your correlation is always going to be 1. All right, so we have R equal to 0.8, N equal to 4 observations. We'll go ahead and punch this in. T is 0.8 times the square root of 4 minus 2, 1 minus 0.8 squared. You get 0.8 times 2 divided by 0.8 squared is 0.64. 1 minus that is 0.36. I need my good calculator. Okay, so let's do 0.8 times the square root of 2 divided by 0.36. Okay, no, that's not helpful. Okay, 1.886. 1.886. Okay, and we have degrees of freedom equal to n minus 2. We have 2 degrees of freedom. And then our alternative is rho not equal to 0. So this is non-directional. Okay, so we'll double the tail area for the p-value. All right, let's go to our reference table. All right, T table, where are you? Okay, T table, 2 degrees of freedom, 1.886. This is always so exciting because very rarely do we get the exact number in the T table, but we got it this time. Okay, so and rather than saying the tail area is between 10% and 5%, now we can finally say the tail area is exactly 10%. Okay, well, I was excited that that's happened. Okay, so the tail area is exactly equal to 10%, and we double our tail area for our p-value. And so our p-value is going to be exactly equal to 20%. 20%. Okay, so if alpha is equal to 0.05, we do not reject the null hypothesis. We don't reject the null hypothesis. And that means we do not have evidence that the correlation in the population is not 0. Okay, And perhaps the word here is we do not have enough evidence to say that the correlation in the population is non-zero, right? Because we saw the number 0.8 and we felt like, oh, 0.8, that's like super far different from zero, right? It's pretty close to 0.1 and we feel pretty good about that. So I think a lot of you, when we had that informal survey, a lot of you said, oh yeah, it's going to be significant. Well, the issue is we only have 4 data points, right? And so you could imagine, right? You could blindfold somebody, give them 4 darts, and just say, throw them at the wall, right? If this person throws 4 darts at the wall, do you think the 4 darts could end up forming something that looks a little bit like a straight line? And if you were to put them on graph paper and calculate the correlation, could you get a correlation of 0.8? And it turns out the answer is yeah. With only 4 darts, something like that could easily happen. You could get a correlation of 0.8. And that's going to happen around 20% of the time, right? So we only have 4 points, and it's not unusual for 4 random points to have a correlation of 0.8. Now, if you had like 10 points and a correlation of 0.8, then almost certainly that's going to be very significant. Okay, so calculating this statistic, n is used in how big your n is. So if you have a lot of points, your test statistic t is going to be large. Okay. Okay. How's that? All right, let's keep going here. And let's talk about linear regression, which is about finding the best fit line. Okay, and so my values, we're going to just use the same simple data set. Okay, and here, now I'm going to just, to make it kind of silly, and give this a little bit of context, rather than just calling it X and Y, we'll say X is the number of bedrooms in some dwelling, and Y is the number of closets in said dwelling, okay? And the question is, which line is the best fitting line, okay? And so I have a few proposals here. I clicked something. I want that, okay. So I want, so here's one possible line. Right, so if you had to fit a line to the 4 data points, do you like that line? Do you like this line? I'll give you equations for each of these also. And or do you like this line? Okay. All right, and so I cheated, not cheated, but like I already know the answer. And so I specifically chose a few lines here that that I know calculates. So here we're going to say the prediction line y hat is equal to 2 times x. Here the prediction line is y hat is equal to 1 plus 1.6 times x. And here y hat is equal to 2.5 plus x. Okay. All right, so which is the best prediction line? Which line is best? Okay. What do you guys think? What would you prefer? So for this one, you can give me a thumbs up. This is my attempt at artwork here. This one you can give me party hat or party streamers. And this one, what's the other one? We'll do the heart emoji. Okay. All right. So what are your votes for which line do you think is the best? Okay, we got one party hat or whatever this, one ta-da, one thumbs up. Oh, you guys already okay, 7 thumbs up, 8, 9. Oh, okay. Well, it's pretty close. We got 10 ta-das, 10, I think 9 thumbs up, something. Okay. No hearts. That's all right. Okay. So what we're gonna do is to evaluate the line to determine which one's the best. We look at our residuals, okay? Okay, and the residual is going to be the actual value, the actual y value, minus the value predicted by the line. Okay. Symbolically, we say the residual for point I is y sub I minus y hat sub I, okay? Where y is the actual value and y hat is the value predicted by the line. Okay, so let's, so we're gonna look at the residuals and we're gonna do what's called least squares regression. Okay, and least squares regression means we want the least amount of squared residuals. Okay, so sometimes you'll hear the term, you know, when we're talking about linear regression, they'll say something like least squares regression or ordinary least squares regression or something like that. And what they're talking about there is we want the least amount of squared residuals. Okay. All right. So let's explore our first line here, which is this one. We might only have time to look at a couple of these lines. All right. So here, here is my x. Let's do x, y. Y hat, the equation here is y hat is equal to 2x. We'll calculate the residual, which is y minus y hat. And we'll have the squared residual. All right, so we got 1, 2, 3, 4. The true values are 2, 6, 4, and 8. Okay, so according to the line, if we plug in y hat for this, I should predict 2. For 0.2, I should predict 4. 3 times 2, I should predict 6. And for 4, I should predict 8. Okay, so the residual is the difference between the actual minus the prediction. I have a residual of 0. 6 minus 4, I have a residual of 2. 4 minus 6, I have a residual of -2. And 8 minus 8, I have a residual of 0. All right, my squared residuals, 0 squared is 0, 2 squared is 4, -2 squared is 4, 0 squared is 0. And so my total squared residuals, total, I should say, of squared residuals is 8, right? 0 plus 4 plus 4 is 8, okay? So that's what we have there, okay? And what we can visualize this, Here I'm going to draw little squares for the residuals. So there's no difference here, but here I'm going to draw a square going from the dot to the line. Okay. And so this length here is 2, and the area of this square is 4. And this length is 2, and the area is 4. Okay. And there you have it. Okay, so that's our first one. Let's go ahead and take a look at let's look at the other one. Let's look at this line. It's here. Yep. Okay. So we're gonna do the same thing. Am I able to copy this? Oh yes. Please work. No. Why doesn't this work? Oh, you know what? I have to do this. Name business. Which layer is it that I want? I want this one. Paste, please. Okay, yes. All right, so we're gonna do that. And okay, and we got 1, 2, 3, 4, 2, 6, 4, 8, and this prediction line is something different. This prediction line is 1 plus 1.6x. Okay, so this is y hat equals 1 plus 1.6x. All right, so if I plug in 1 into here, the line, the value I predict is going to be 1 plus 1.6 times 1. And I get 2.6. All right, the next value is 1 plus 1.6 times 2. I get 4.2. Here I get 1 plus 1.6 times 3, and I get 5.8. And I get 1 plus 1.6 times 4 is 7.4. Okay. All right. And so now let's calculate. Sorry, it's my daughter just got back from, I think, McDonald's or something. But okay. We'll calculate the residuals by doing y minus y hat. I get a negative 0.6. 6 minus 4.2. I get 1.8. 4 minus 5.8 gives me negative 1.8. And here, the actual value is 8. The predicted value is 7.4. We get a residual of 0.6. Okay, and if I square these, then 0.6 squared, negative 0.6 squared gives me 0.36. This gives me 1.8 squared. I did the work before, is 3.24. This will give me positive 3.24, and 0.6 gives me 0.36. And you know, one thing is squaring the residuals has the effect of punishing big mistakes more heavily than little errors, right? It has the effect of, quote, punishing big errors more than little ones. So if you have if you have squared residuals, it's much worse to have one error, one residual that's of 10 that's squared than to have 10 residuals of 2. Okay, because one residual of 10 squared, that is 100. Okay, 10 residuals of 2, so 10 residuals of 2, you know, adds up to 20, which you feel like, oh, that's more than one residual of 10. But if you square them, 10 residuals of 2, there's 2 squared into 4, and 10 residuals of 2, if you square them and add them up, you would get 40, okay? And that's less than 1 residual of 10 squared, which is 100. Okay, so anyway, when we do this, the total is going to end up being 7.2, right? And so the picture here is if I draw the squares, you know, much in the same way that I do here, this time taking each, where'd it go? Am I doing something wrong? That looks right. Okay, there we go. All right, so here is the square. Here's a square. Here's a square. Oops. And here's a square. Okay, so each of these, we're looking at the, you know, this distance is 1.8 and the area is 3.24. Okay, and this, the area here is 0.36. And so the total area of their squared residuals is 7.2. Okay, so if you take the areas of these squares, you get 7.2. And so if you compare 8 to 7.2, 7.2 is less than 8. And that means y hat equal to 1 plus 1.6x is the better line. Okay, all right, we're not gonna have time to go over the kind of the third example, but if you did the work there, you would get even larger, larger residuals, larger total squared residuals. Okay, so we're going for the line that has the smallest total amount of total squared residuals. Okay, so how do we get this? Well, you don't have to just try out a whole bunch of lines and see which one has the smallest amount of squared residuals. The other people have worked this out. And so for linear regression, the best fitting line will always have the following slope and intercept, okay? The least squares regression line will always have the following slope and intercept. Okay, the slope, and we use the symbol B1, is going to be found by taking R times the standard deviation of Y divided by the standard deviation of X. And the intercept, which has the symbol B0, is found by doing Y bar minus B1, the slope, times X bar. So you must find slope B1 first. Okay. The best fit line will always pass through the point X bar comma Y bar. Okay, so when we had our data X and Y, 1, 2, 3, 4, 2, 6, 4, 8, you know, our mean is 2.5, our Y bar was 5, the standard deviation of X was 1.291, the standard deviation of Y was 2.582, and then the correlation is 0.8, right? So these are your summary stats. So the slope B1 is just a matter of plugging in these numbers, 0.8 times 2.582 divided by 1.291, and that gives us 1.6. The intercept, B0, it's going to be 5 minus B1, 1.6 times X bar 2.5. That turns out to be 1. And so our prediction line which is y hat is equal to 1 plus 1.6x. Okay, so prediction line is y hat is equal to B0 plus B1x. Okay, and you just plug in the B0 and B1 that you get. Sorry, I'm going to, got to go a little bit quickly to kind of just make sure I get everything in here. Okay, so what we want to do, let me go ahead and give you your last view quiz answer. Last view quiz answer is the letter A. A as an apple. A as an apple is your last view quiz answer. All right, so basically to make predictions, just plug in a value for X and get a Y hat. Value for X to get the prediction Y hat. Okay, so if a place has 2 bedrooms, how many closets do we predict? Okay, so we have y hat is equal to 1 plus 1.6x. So we're going to get y hat being the closets. 1 plus 1.6 times 2. We predict it has 4.2 closets. Now, of course, a real place is only going to have either 4 closets, 5 closets, 3 closets, okay? It's okay that the prediction has a decimal. Okay. And the idea is that if you looked at a whole bunch of places and recorded a whole bunch of places with 2 bedrooms, some will have 3, some will have 4, and you recorded all of the different number of closets you see. So I'm sorry, places with 2 bedrooms, some will have 3 closets, some will have 4 closets, some will have 5 closets. And the idea is if you looked at a whole bunch of them and you took the average, that average might be 4.2. And so that's going to be our prediction. Okay, let's, you know what? Let me, just in the interest of time, I'm going to pull up, I'm going to type everything out in a word processor just because I can type a little bit faster. I know if you're taking notes right now, you can't keep up with me typing. But I'll just, I'll copy and paste this into the notes here. Okay, so let me just write interpretation of the slope. Okay, so B1. Okay, the slope is how much our prediction for y will change if x increases by 1. Okay, so the slope is 1.6. Okay, so that means if x bedrooms goes up by 1, our prediction for the number of closets goes up by 1.6. Okay, now don't think of this as changing x. Okay, changing an observation's x value, because you can't like if you're doing snake length and snake width, you can't just suddenly like stretch out the snake and make its X value bigger, okay? Or you can't just take a dwelling and add a bedroom and make its X value bigger, okay? The slope basically describes the difference between predictions that we would make for two observations with different X values. So it's just if one observation has this X value and another observation has this X value, how much would you predict for this observation and how much would you predict for this observation? That difference will be determined by the slope. It's not that you're going to take somebody and change that person's X value, which in many cases is not going to be possible. Interpretation of the intercept, okay, which is B0. In our case, B0 is 1, okay? This is our prediction y if x equals 0, okay? In some cases, it makes sense for x to be 0. In some cases, it does not. So for us, you know, how many closets predict dwelling 0 bedrooms? Okay. We predict 1 closet. Kind of actually makes sense, right? Could work for like a studio. Okay. But if we're doing something with like snake length, okay, not work for snake length, snake weight. You can't have a snake with 0 length, right? Snake with 0 length is literally no snake, right? So that's not going to work. So we can't do that. Okay. Well, there's a section, you're gonna have to read the textbook on R squared for the coefficient of determination. This is in the textbook, all right? And there's a few warnings that I didn't get to make, but basically the important thing is this stuff only applies for linear relationships, and don't extrapolate. I can talk about extrapolation on, I guess, next Tuesday's lecture, okay? So we'll say don't extrapolate, and I didn't get to get into that, and only apply to linear relationships. I guess I'll cover warnings on Tuesday. But I'm already over my time, so we'll call it a day here. We'll end here. Have a good weekend. Again, you'll have your last quiz, which will cover chapters 11 and 12 this weekend, and you can expect to see that posted on Sunday as usual. Okay, have a good night, everybody. Have a good weekend, and we will see you guys on Tuesday.